Hey Wheat North, Mr. Yergler here to talk about heat and heat transfer. I'm going to focus on the particle aspect of heat before we kind of get into any type of calculations or anything like that. All right. Remember that in chemistry, heat is always the transfer of energy. Okay, so nothing really has heat. You can only transfer heat. So let's look at some examples of this. This is a great illustration or animation. Remember that heat is the transfer of energy. So heat is being inputted here into this molecule, and the only way for it to transfer its energy is to bump into other molecules. Remember that all these molecules are kind of always vibrating. The stationary ones are just vibrating a lot slower, right? And as things heat up, as things gain energy, they vibrate faster. So that vibration is transferred to the neighboring particles, okay? And that's how heat kind of transfers from one particle to another. They just run into each other more. Here's another example. Think of this as like a rod of metal or something in a flame. The flame is inputting heat into this end of the metal, right? And as these particles start vibrating more, they transfer that energy by bumping into each other, and the energy or the heat slowly transfers across the piece of metal. Okay, let's focus in on one specific molecule. So right now he's stationary, and think about it this way. The energy that he attains, or the energy that he absorbs, can only come from his neighbors, correct? Without that transfer of energy to him, he doesn't gain any energy, right? Similarly, the energy that he releases or that he transfers away is the same amount of energy that his neighbors absorb, right? Now this is kind of complex in this picture because he's transferring energy to this one and to this one and to this one, and probably some back to the other ones as well. So it's going in a lot of different directions. It's not perfectly linear in this example. But think of it, you just have to catch this idea. This is a really important idea. The energy that he absorbs, or the heat that he absorbs, is the same amount of heat that is given off by his neighbors. And likewise, the amount of heat that he gives off is the same as the amount that his neighbors absorb. Okay, let's look at another example of this. All of these particles, when I start the simulation, all these particles will be stationary. They're blue, indicating that they're really cold. They don't have a lot of energy. There's one really fast moving particle right here, and he's going to transfer his energy to his neighbors, just like in the last example. Here we go. Ready? So notice he goes really fast at the beginning, right? And as he bumps into other particles, all the other particles start bumping into each other and transferring that energy. Now focus on this point right here. The total amount of energy has not changed, right? We started with one particle moving really, really fast, and now we have a bunch of particles moving kind of fast. So this is what we'd call a closed system. There's not any energy, there's no heat escaping this box, right? All of the heat transferred from any one particle is the same amount of energy that's absorbed by the particle that it collides with. So the heat lost by one object is the same as the heat absorbed by another. Okay, that's a very important point that we're going to focus on more. This idea is very tangible when you're drinking a hot beverage, for example. So I like to kind of sometimes imagine that I have a nice cup of tea right here, like this. Now think about this. This mug feels really hot right now, as you have experienced before, right? Where does that heat come from? Why does the mug feel hot? Well, obviously, it feels hot because the tea inside is hot, right? But how is the mug hot, the outside of the mug hot, if there's no tea getting out of the mug and the source of the heat is in the inside, right? How is it that the outside of the mug right here feels warm because there's something on the inside, right? There's no tea traveling through the mug, right? Let's zoom in and look at the particles. Ready? Here we go. Here we have the particles of tea inside the mug, and then the mug itself, and then the air outside the mug, right? These tea particles, or water particles, since it's mostly water, have a lot of energy, right? They're really hot. They're flying around. They're moving around really fast. They have a lot of energy. As they bump in to the particles in the mug, those particles then in turn move fast as well, right? Now, not fast enough that they are going to melt or anything. That would require enormous temperatures for ceramics. But that energy is then transferred to this molecule and to this molecule and then to this molecule and then to this molecule. And as that energy is transferred, eventually the outside of the mug also feels hot. So when you go to touch it, the energy from those molecules is now being transferred into your hand, which is why you feel heat. Okay? So there's not really any such thing as cold. There's just a lack of heat, right? So these particles, they're air particles. They're moving around, but they're not real warm, right? They're cold particles. They're not transferring their coldness into the mug, right? When the tea cools down, it's not that the air has transferred its coldness into the tea. It's that the tea has transferred all of its heat out into the air, and thus the tea has cooled down, right? So there's no such thing as coldness, but there is a loss of heat, okay? Now, let's focus on this point right here. The amount of energy that the tea gives off to the mug is the same amount of energy that the mug absorbs from the tea, right? So the heat lost by the tea equals the heat gained by the mug. All right, let's look at this way. Let's imagine you have a compartment of hot water and cold water, right? Hot water particles are moving very fast, and just like the tea in the mug, they transfer that energy through the molecules in this little barrier here, this thin metal plate, and that energy is then transferred into the cold water, where those molecules begin to speed up, okay? Now, what happens to the temperature of the two sides? Over time, that energy from the hot water will transfer through the metal plate into the cold water, creating more energy in the cold water, right? Those molecules bump into each other, they add more heat, they add more energy, and the temperature starts to rise. Eventually, the two temperatures will be equal to each other. And whenever they're at the same temperature, we call that equilibrium. And especially in this case, it would be called thermal equilibrium. Thermal meaning temperature, equal temperature. Everything is always trying to get to equal temperature, or equilibrium. So heat is always transferred from hot objects to cold objects because they are trying to get to equilibrium, right? It's impossible for a cold object to transfer energy into a hot object because the hot object already has a surplus of energy. It's going to lose that energy and heat up the cold object. One piece of equipment that we can use is called a calorimeter, and this helps to determine the amount of heat transferred from one substance to another. Now, is all of the energy in your cup of tea or in your cup of coffee, is all of it going into the mug? No, not really. There's lots of energy that's going out the top. So we can't really say that the heat gained by the mug is the same as the heat lost by the coffee or tea. But that's only because we don't have a closed system here. We're letting a lot of energy escape out the top of the mug. But what if we contained it so that there wasn't any heat lost to anything other than the mug? That's where we would use a calorimeter. So in a calorimeter, it's perfectly sealed and insulated so that all of the heat gained by an object is the same as the amount of heat lost by another object. Okay, we put two things in there at different temperatures, they transfer energy, and because we're assuming that no energy is lost to the surroundings, for example, in a styrofoam cup, styrofoam can insulate against temperature changes. So the styrofoam prevents heat from being lost through the cup, and then we cover it, to help keep the heat inside. So we're kind of assuming that all of the energy lost by one thing is gained by another thing, okay? And in a perfectly insulated container, like a calorimeter here, that would be true. So this is what I want you to make sure you understand. The energy lost by the hot water is equal to the energy gained by the cold water. And this could be anything. This could be lost by the hot object. It would probably be a better description to say a hot object equals the energy gained by a cold object when they're in contact with each other. Now we're putting an asterisk next to equals because this is only if it occurs in a closed system, right? If we can guarantee that there's no heat loss to the surroundings, then we can say that the energy lost is the same as the energy gained, okay? Now this is where everyone gets confused, so make sure you understand this. The negative here is not a mathematical negative. I mean, we're going to treat it as a negative in our calculations, but negative Q means energy lost. Okay, write that down. Negative Q equals energy lost. The negative means the energy is leaving the system. Okay, so in our T example, T has a negative Q because it's losing heat, and the mug has a positive Q because it's gaining heat. So mathematically, this doesn't make any sense. Negative Q equals positive Q. That's not true in math. But in chemistry, we're using negatives and positives to indicate the direction of heat transfer. Heat leaving is negative, and heat gained is positive. Now moving forward, we know that Q is equal to MC delta T, and so we can actually substitute in MC delta T on both sides of this equation. We'll get to that more in the future, but this is the main idea that I want you to make sure you understand. Heat lost is equal to heat gained. Okay, even though this mathematically doesn't make a lot of sense, we're only using those negatives and positives to indicate the direction of heat. Heat lost is negative, heat gained is positive. All right, if you have any questions or if you're confused on anything, make sure you write that down right now so that you can ask that question in class tomorrow. This is Mr. Yergler signing out.